OSI model was developed by the International Organization for Standardization. It was used to help organize and identify standards for communications from one device to another. And they have split up. Now, this is just a model. It's nothing physical. It's not a piece of software that we install. It's just a concept that we utilize to troubleshoot, to solve problems, and help us understand when we're learning how these devices communicate, what all is required. And it's split up into these 7 layers. And it starts out with layer 1 down at the bottom, the physical layer. The physical layer is the physical aspects of our network that we have, the cables and such. And then we go to the data link layer. The data link layer, and we're going to get each layer details here, but the data link layer, yes?
I didn't get a sheet.
You didn't get a sheet. Well, here's a sheet right here. The data link layer identifies the physical addressing, the physical aspect of our network location. Because the concept of having a network is sharing resources. And if you're sharing resources, there's got to be other devices or other resources besides yours on the same network that are connected. So we have a tablet, a computer, and a printer all in the same network. Those 3 devices need some sort of physical addressing in order to keep them separate. So when they communicate with each other, they know who they're talking to. Just like all of us in this room are in the classroom network, but we have physical space that we take up, or physical address, location where we're at, so we can then direct communication to each other or to the group. So that's the concept that this works. That gets us into the next layer, layer 3, the network layer. The network layer is going to help us logically organize us into a grouping. Okay? That is called a network. So the logical grouping for us here in this example would be the classroom itself is a network. The classroom next to us is another network. So that's our logical grouping. Although you can get up and move to another classroom, you can make a computer or a device part of another network. It's a logical thing, not a physical thing. Okay? Then we move up to transport layer. This is where we can identify how we receive and send information. An example using our classroom and our bodies as this example, you can receive information through your eyes, through your ears, through your nose, right? There are 5 senses. Those are the TCP port numbers. That's how you get information and how you give information with your body gesture and with your mouth by verbally expressing it. That's how you're sending information. So TCP port numbers and UDP port numbers are used there. Session layer. What's that? Your question?
That's the TCP.
That's where TCP and UDP exist. You betcha. Yep. We're going to detail on each one of these. I have a slide on each layer.
Okay.
Just giving a quick overview. Session is, we've established a session, meaning class started at this time, and I'm gonna keep it going, and when we're done, we're gonna terminate it at 2:20. And then the presentation is, what does it look like? What is the data, the information that we are trying to transmit, what does it look like? Is it a text? Is it JPEG? Is it a MPEG? Is it encrypted or compressed? So you have different options on how the data is presented. And then the application is the actual program that is invoking or making the connection from one device to another. For example, of an application would be HTTP. What is that? Hypertext Transfer Protocol. This is a web browsing, right? So the web browser itself, Internet Explorer, Mozilla Firefox, that's not the application. The application is HTTP or HTTPS. Okay? So application does not refer to the piece of software that we install on the computer. It is the protocol and how we are going to make the connection to the device and the set of rules that we have to follow in order to make that connection and allow one device talking to another. All right, so Why a layered model? It reduces complexity, standardizes on interfaces. So I can have an Intel network card or Intel wireless network card installed on my computer. And I can have an Apple wireless airport access point, wireless access point. I don't need to have an Apple wireless card in order to communicate with the Apple wireless access point, because they've standardized on how these devices are supposed to communicate together. So we have interoperability between these devices. And when Apple manufactured this wireless access point, they didn't have to think, well, there might be a 3Com wireless network card. Okay, if there's a 3Com wireless network card, we're going to have to make these changes when we manufacture these. They didn't have to think about that. Okay, they only had to follow the standards for Wi-Fi. And if they did that, then any wireless network card, even a brand new one that doesn't even exist yet, when it's manufactured, will work with an Apple or a Cisco or an HP wireless access point. So that's the goal of standardizing interfaces and even protocols on how we communicate. And then engineering these devices and allowing for backwards compatibility and moving forward with new technology. It also allows us to use this. Now, that gets us into the application layer. So let's get into more detail on this. So I mentioned before that the application is not necessarily the piece of software that we install in our computer. That piece of software that you install in the computer is your interface, your means of invoking or starting that application to make a connection to a remote computer. So that program, you would probably start up Mozilla Firefox, a web browser. And the application that you're going to invoke, or the application you're going to start, is the HTTP application. Okay? That's the responsibility of the application layer. There's a lot of different processes that are used. Yes?
Aaron, I thought HTTP was a protocol.
HTTP is a protocol, but HTTP is also an application. Let me kind of clarify it. You are exactly right. HTTP is a protocol, hypertext transfer protocol, right? But it's also a network application, meaning that it has a certain set of commands and functions that it does and uses the IP protocol stack in order to accomplish its task. And its task is simple. And you can actually, from the command line, you don't need a web browser to invoke the HTTP protocol. From the command line, you can actually telnet into or connect to a server, and you can manually type the commands that the programmer that created the web browser is actually telling the web browser to do. Okay, so when you type in a web address like www.yahoo.com, you just type that into an address bar and you hit enter. You don't type any other commands, do you? The web browser has a list based on the HTTP protocol of what commands it needs to send to Yahoo's server in order for the Yahoo server to go, oh, you want to look at my default website or my default web page. Well, here's the default web page. And then the web browser gets all of this data from the server and will display it in the order it's supposed to. Does that make sense? Does that answer your question?
Oh, yeah.
Okay. Okay. Any other questions regarding this? That was a good question. So you're gonna see that the examples I give on each one of these layers is going to be either a protocol or a standard. And again, the reason for these layers is for us to see how these protocols and standards are applied or used within a computer system. When I'm talking computer system, these mobile devices and cell phones, they're computers. Anything that connects to a network. Okay? So, next one, the presentation layer. how the data is represented. Examples of a presentation layer would be encryption and decryption occur here. And in the days when we had really slow internet connectivity, compression and decompression was done here as well, because we would try to compress the data we're about to transmit because we have slow internet connection or slow network connection. So it tries to compress it, send it to the receiving party, and the receiving party then would decompress it. So the responsibility of that is laid upon the presentation layer. Now, the HTTP protocol has all of this built into it. It does the compression, decompression, the encryption, the de-encryption.
That'd be opening the packet that actually contains this information.
Yeah, so the HTTP protocol, the HTTP application, would then open up or uncompress a compressed file and then display it in the web browser. Or when it receives a JPEG, a picture of my smiling face on my website, it will then render that picture and display it within the web browser. Does that make sense? So an example of presentation would be JPEGs or GIFs or PNGs. Okay, so here we have ASCII is another type of presentation layer. The American Standards for Character Network Interexchange. I think I got that acronym right. I probably got off by one or two words there, but ASCII. ASCII is the American Standard Coding Interchange, something like that. So ASCII, JPEG, encryption, decryption, compression, decompression, what the data looks like. So obviously if we're looking at a web page, it's going to be a bunch of JPEGs and some ASCII text, right? And maybe some of the JavaScript and the codes and such, that's all ASCII text, and then the web browser itself will actually execute that code and display whatever it needs to display in the website. Then we get to the session layer. The session layer provides inter-host communications of three things that occur here: establishing the session, maintaining the session, and terminating the session. And those are the three main things that occur here. Some protocols that their focus is at the session layer are things like NFS, the network file system, being able to access a file share on a computer through the network and being able to write files over the network onto that remote computer. That's NFS. So that's establishing the session with the server, being able to maintain it while we're writing data to the network share or reading data from the network share. And then when we're done, terminating, saying, I'm done communicating with you, we're going to close this session. Next time I communicate with you, we're going to open up another session, and it will essentially have another session ID. Okay, so each session has its own process that it does in order to keep the dialogue going. AppleTalk, which isn't used much anymore, but RCP is used a lot. The X window, those in my Linux class, we talked a little bit about X window, and you probably read about it if you've been reading the assignment. SQL, those in database concepts or database class will be working. Those in the web analyst programmer, you're going to be working with SQL, the SQL query language. MySQL is a very popular open source database software that's used out there. So doing kind of SQL queries, that's a session layer responsibility. And that is the protocol that's responsible for maintaining, terminating that session. Okay. Are we all kind of seeing this concept? As we move lower and lower through the layers, we now get to the transport layer. The transport layer is where we are going to provide reliability. This is where we now have the top three layers are primarily the application itself, ensuring that we are establishing a connection, following certain rules, and are going to establish a session that we're going to be sending data and what the data looks like. Now at the transport layer is where TCP really takes over, or UDP. This is where TCP ensures that the data that's sent makes it to its final destination. Or in turn, if it's using UDP, if it's sent, that it really doesn't have to care if it was received or not. So the reliability, flow control, and error correction. How does that work? TCP and UDP are the primary protocols that are used at the transport layer. And their responsibilities. TCP has what we call a three-way handshake. Before I communicate with you, I'm going to ensure that I have your undivided attention. So I'm going to go, Terry,
Yes,
I'm going to talk to you.
what would you like to say?
Now that was a three-way handshake. We now have focused on each other, and now we're going to be transmitting the data that we need to send. And where is that data going to be coming from? It's going to be coming from the upper layers. The data comes down and goes, hey, we need to talk to this server. So now TCP goes, okay, I'm ready. I'm going to talk to this server. And then they get the server's attention. And then the server responds. And it goes, okay, I'm going to start transmitting data. And here it comes. And it starts flowing. So that's where TCP ensures that everything is sent. Terry, did you get that?
Yes, I did.
Okay, I'm sending you some more. So TCP, we organize TCP by using TCP port numbers. And on the little study guide, we have the TCP port numbers. Terry, did you get that?
Yes, I did.
Okay, so that's how TCP works, is it sends a little bit of data and verifies. Did you get that last bit?
Yes, I did.
And then we continue on. So TCP is constantly doing that. UDP, on the other hand, user datagram protocol, doesn't care. It transmits the data and assumes the receiving party got it. Why do you think we'd want to have a protocol like that?
Streaming videos.
Streaming videos, continuous flow, speed. Give me the data as fast as you can. If I didn't get it, the application will whine about it, and the user will have to hit retry, and then it'll go back and do it again, right? We want to get the data as fast as possible. That's where UDP comes into play. One example of a UDP type of an application is DNS. You guys remember DNS? Domain Name Service. When you type in yahoo.com into your web browser, it has to be translated into a IP address. That's what DNS does. So that query to the DNS server is saying, hey, what's the IP for Yahoo? Instead of waiting and waiting and waiting and waiting for the IP address translation to come back to you, we use UDP because we want to make that as fast as possible. We need to translate that name into an IP as fast as possible. And if it doesn't work, what happens in my web browser? Failed to load. It times out, right? So then you as the user go, and you hit retry, right, or refresh, and then it will hopefully go through the second time. So that's where UDP comes into play. We try to get as fast as we can. So UDP doesn't acknowledge receipt of packets, where TCP does. Every couple of packets, and that depends on the windowing size. That's another term to be thrown around you might see. It will verify. So for an example, I'll send packets 1, 2, 3, and then I'll ask Terry, acknowledge 4. And then Terry will say, yes.
Yes.
And now I'll send 4, 5, and 6. I'll say, acknowledge 7. And Terry will go, acknowledge 5. And then I'll go, wait a minute, he didn't get my last 2 packets. So then I will now correct the problem. TCP goes, wait a minute, didn't get those. So we'll send 5, 6, and 7. And Terry will go acknowledge, then I'll go acknowledge 8, and he acknowledges 8, and then I start sending more. So that's a window size of 3. So if we're having a lot of errors, and there's the network is a very poorly constructed network, we might have a window size of 2 or 1. If it's a very fast network and not a lot of errors, we could have a bigger window size, meaning I don't have to ask every single time and verify that the packets were transmitted. How are we doing so far? Good? Yes.
Why would the computer not receive the packets?
A lot of reasons.
I mean, it's because
One,
of the
you
size
stepped
of
on the
it.
cable,
Oh,
and it got disconnected, you went, oh no, and you quickly plugged it back in, right? That's one perfect example. Another one, the router's job, and the router is the device that connects one network to another network. And we know the internet is a big, large, the largest network that has ever existed in human reality. And it connects one network to another. So the internet is a connection of networks. And to connect these networks, we have routers. So if you want to communicate to Yahoo's website or Google's website, you have to go through multiple routers to get to wherever Google's servers are. So routers have a rule that's built into them, the software that says, if I get overloaded with packets, too many packets are coming in, I'm going to just discard a couple of them.
Oh, okay.
Does that make sense?
Yeah, no, it does.
Okay, because routers, their focus is at the next layer, the network layer. And at the network layer, IP doesn't give a crap if your packet makes it there or not. That's why we have TCP. Because IP's primary responsibility is to organize our networks and make sure that we can communicate from one network to another. So if the routers, whose job is to create these networks, gets overrun, it goes, yeah, I'm going to toss a few of these because they're just too much. My buffer is filling up. Serious, we'll discard them.
Is it the same error if it's corrupted?
Yes, there's another issue, and that could happen even at the lower level, like a data link or physical layer, is it's corrupted. Or if it's a wireless transmission, if there's a lot of errors, the packet will just get dropped altogether. Yeah, so there's a lot of reasons why it'll get dropped. Okay? Or it could just be Terry's computer that I'm communicating with. Terry just might be overrun, or his software that he's running might be corrupt. And it might just be slow that it can't just grab all of those packets, and it's not acknowledging it. So, a lot of different reasons. That's why we have jobs as network administrators, because we can try to solve those problems and identify. Oh, we got to update Terry, right? So that helps us identify those things.
No kidding.
Network layer. This is my favorite network layer. Probably why I'm a network instructor. It is responsible for the logical design, logically separating all of these devices that we want to communicate, logically creating little groupings of these devices into what we call networks. It is responsible for path determination. You guys are familiar with traceroute, right? What happens when we type traceroute at the command line?
Traces all the
It
routers.
traces all the hops. And when you traced hops to a website, was it identical for the person sitting next to you? They traced hops to that same website? Not necessarily. Sometimes, yes, most of the time, but not always. Because there's more than one way to get to Madison from Fenimore, isn't there? Right? I can take Highway 18, right? I could also go down to Platteville and take 151, right? So there's many ways that I can get to Madison. Think of the internet or all of these interconnected networks just like a road system. There's going to be some roads that are faster than others. There's going to be some roads that are more direct, go through less cities than others. That's exactly it. So imagine a city is a router. You get into the city and there's signs and directions telling you if you want to go this direction, go here. So once you get into a city, then you have multiple roads to go other locations. Okay? How's that concept? Is that picture working for you? So some of the protocols that exist on the network layer that focus on logically addressing and path determination are IP, obviously is one of them. IPX, which is hardly ever used in AppleTalk and DECnet. A lot of these protocols existed 10, 15, even longer ago that have been kind of turned off because they weren't that popular. And IP became the standard because of the internet and the internet's popularity. Instead of having a separate protocol here for our computers, and then we connect it to the internet. Now we have to translate our protocol that we use to IP. The manufacturers of this software and operating system decided, let's just stick with one standard network protocol, and we'll use IP because that's what the internet is and that's what everyone is using. So AppleTalk, IPX, and DECnet kind of got depreciated and aren't used anymore. But IP has become the standard routed protocol. It's routed because routers routed. It's a routed protocol. Path selection is done by routers using routing protocols. Examples of routing protocols. This is pretty much the routers talking to each other. Because I don't know that Lancaster is, what highway goes between Fenimore and Lancaster? What is that?
61.
61. That in Fenimore here, we don't know that Lancaster exists over there unless Lancaster said, hey, we are over here on Highway 61. That's how you get to us. So Lancaster and Fenimore, those routers talk to each other. And they exchange information saying, this is how you can get to my city, and this is how you get to my city. And Fenimore tells Lancaster, hey, you can get to Madison from me. And Lancaster goes, oh, cool, thank you very much. I'll add that to my list of routes on how to get to Madison. I also can get to Madison through Platteville, too. Did you know that? And Fenimore goes, oh, okay, I'll add that to my list, that in case I can't get there on Highway 18, I'll use Highway 61 to get to Madison. So that's what routers do. They're constantly talking to each other using these routing protocols like RIP, or IGRP, or EIGRP, OSPF. Okay, so all the routers on the internet are exchanging information using these routing protocols. That's the router's language. And we get into our first physical device.
Yeah.
Routers. Routers work at the network layer. What does a router look like? Do I have one up here?
There's one down here.
No, that's not, I don't like those.
Well, not that kind of room. Not the ones.
Here's a router. This is a router.
That's a very big.
This is a very small router. There are routers that are probably about 10 times this in size. Okay? This is a very small one for usually a small to medium-sized business. And it has ports on the back, and each port would represent a network that is connected to. Okay, and we can add more ports by taking out these right here, these little covers. We can slide in more network interfaces. Okay, so this is the device that we would use. We would use one here in Fenimore, and we'd have another one in Lancaster, and we would connect them through TDS, and we'd ask TDS to get us a T1 line to connect this router to that other router. And then this router would use that T1 line, that WAN connection, to connect to the other router. And that's how the two routers would talk to each other. And then we'd have another connection to a switch, so we have all of our PCs. They would talk to the router would go, yes, I can route your packet for you. I'll route it over to Lancaster, and so forth. Or out to the internet, if I have a connection to the internet and all those networks. So you can pass it around if you want to. And the ultimate question always, well, how much does that cost? Well, that one, I think used, you can get that for about $500. Brand new, I think it was about $3,000. So that's the network layer. IP addressing exists at the network layer. Whatever in time. Good. The data link layer. This is layer 2. The data link layer is responsible for access to the physical media, to the physical cabling, to the physical network card. Okay? It handles error notification. It doesn't care how to fix it. It just says, oh, there was a corrupt frame. Sorry. I just discarded it for you. It doesn't correct it, though. And IP just goes, oh, well, it didn't make it. But then TCP says what?
Send it again.
TCP says, hey, what happened? So it sends it again. Exactly. So it is responsible for addressing the physical devices. So it is this is where we have the MAC address. You see the media access control? The MAC address. The MAC address is the physical address burned onto the network card at the time it's manufactured. I have a really old network card here, and you can see in the top right hand corner, I'll pass this around, you can see the MAC address. And the MAC address consists of 12 hexadecimal characters. The first 6 hexadecimal characters are printed on this actual circuit board, and the last 6 characters are on a little white sticker that's starting to get rubbed off because I pass it around and students chew and lick this thing. So I don't know why, but they insist on doing that. So top right corner, look, you'll see Ethernet address. That's another term for MAC address. You'll see the first part is burned on the board, the other one's a sticker. So all they do is, when they manufacture these network cards, you can just set it back there somewhere. Thanks, Cody. When they manufacture these network cards, each company, Intel, 3Com, Cisco, Apple, they all get assigned the first 6 digits of the MAC address. That's the organization unique identifier, the OUI. Then they can assign the network card that they manufacture any number they want after those first 6 digits. Yes?
Those, any number they want after the first 6, is that generally the serial numbers for that particular card?
It can be, depending on, it's not necessarily the serial number, no. Not necessarily. Serial number is more, the model number is what model or version they're creating, but the serial number is typically for their own inventorying, and the MAC address is unique though. So sometimes they could use that. The MAC address will be unique. There never, ever, 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 even in the future, will there be another network card with that MAC address. They never, ever can repeat them. Yes, question.
Model numbers and serial numbers are made up by the manufacturer, whatever they want.
Right.
The MAC address is a universal standard.
Across the
That can be
whole
issued
earth.
One time and one time only.
Yes, one time only. So the moment that Intel manufactured that card, they assigned that MAC address to that card. They cannot manufacture another Ethernet card with that address.
Nor can anybody else.
Where's that database kept? There are a couple of them on the internet, but you can just do it. You can do a search. So when I do packet capturing and I'm doing some troubleshooting on my network, and I'm trying to figure out what device is sending out all of this garbage on my network, slowing it down, I can capture those packets and I can look at the MAC address of where it's coming from. And I can tell by the first 6 digits, I can look those up. There's a lot of databases on the internet that you can look those up. You can tell the manufacturer and go, oh, it's an Apple device. And then I can more narrow down and go, oh, it's an iPad. So I can specifically identify, well, I've narrowed it down to an iPad in my company or in my business that's generating all this traffic. So that I can help myself narrow down trying to find out what device I need to turn off or configure or change in order to solve my network problem. So yeah, it is very unique. So like the FBI, CIA, they're trying to find out who's doing what on the internet. That MAC address doesn't get transported out to the internet because it's the physical address on the network you're directly connected to. So the address that gets sent out on the internet is probably your router's MAC address that gets used on the internet. But every time it hops to a new router, that MAC address will change. Okay?
So MAC addresses are basically LAN addresses.
LAN addresses only, yep. But the reason why we don't ever manufacture 2 network cards with the same MAC address is that if I had 2 devices on this network right here with the same MAC address, only one of you will be able to communicate at a time because the switch that also functions at this layer, is another physical device, The switch that functions at the data link layer keeps a database or a list of all of the physical MAC addresses that are connected to it. A switch. Here is a switch. A switch is a concentrated device that allows me to connect all of these devices into one central hub that allows me to actually have these devices talk to each other. So this switch keeps track of all the MAC addresses. So if I have, let's say this device plugged in to port 9. Now what it does is it looks at the MAC address that's coming from this device, because this is going to start talking when I turn it on, and it records the MAC address that this device has as port number 9 has this MAC address. So when you want to communicate to this device, this switch goes, oh, that's out my port number 9, and will then forward those bits across this wire on port number 9. So that's how that works. And this MAC address has been gotten scratched off, so we can't see it on this one. But that's where the network card that you have that just got passed around, that's what it is. So this is a switch. My network card. This is cool. The MAC address, if you didn't read the first 6 digits on here, is 00AA00. That's one of the first MAC address OUIs that was assigned to different manufacturers. So this is a really old network card. I think that's a pretty cool artifact. I'm glad I have it. I have one of the first Cisco routers too. It's back there in my cabinet. Not the first one they manufactured, but the first model that they started distributing. It's pretty cool. We have a couple different media access. Deterministic, which is token passing. That's where we had old token ring networks. Token ring network, we had the devices were connected in a ring. Really interesting. So each device was connected to the next device next to it in a ring. And they did just that. They passed a token. Imagine a token like a basket. Like a nice little underwater basket, weaving basket thing that you'd make. And that basket then gets passed, and it's empty. It gets passed to the next device, and to the next device, until this device goes, oh, I got some data to send. It will then fill that basket up with bits, and those bits will then get sent to the next device. But those bits are addressed to a computer. So we have computer A, B, and C. So that basket gets sent and addressed to C. So it goes all the way around and gets sent over here. It doesn't send it this way. It keeps sending it in a circle all the way around. So B gets it and goes, hey, this basket is addressed to C, not to me. I'll just pass it on. That's what they call token passing. And this computer gets the basket and goes, hey, I got something. It's addressed to me. Opens it up, reads the data, sends the token on its way. The empty token goes around until the next computer needs it, and so forth. That's token passing. That's deterministic access control. And then we get into a non-deterministic. Non-deterministic is a bus network. And that is what we use today. This is what we use today, where each device shares a media. They share a wire. Okay? Ethernet. And token. Ethernet is what we use today. But what we've done is, instead of having one bus with one wire is run here, we now have replaced that with a switch. That's what we have today, and that's the device that's getting passed around right now. So why they say it's a broadcast topology means that when this computer wants to communicate, it sends out a message onto the wire, and everybody gets it. And we'll get a little more detail on that later. Let me get this last layer in. I'll let you guys go because I know class is over. The physical layer provides the electromechanical aspect of networking. The actual physical wires. What wires am I using? Am I even using wires? Am I using the atmosphere to send a radio frequency signal? Am I using coax or fiber optic? Okay, so that's where the physical layer comes in. Identifying the actual standards, the the EIA, TIA standards on the type of wiring that I'm going to use. Cat 5 or Cat 6 are some other industry standards on identifying what type of cable am I going to use is going to determine how fast my network will communicate. Okay? So that happens at the physical layer. That worksheet that you're working on, if you for notes, I'm not collecting yet. Keep that for yourself, for your notes right now, okay? There's some other aspects in here that on that worksheet that we haven't talked about. We'll get into that and discuss that later. Okay? So, any other questions about today?
Is
Yes.
physical best represented by a network card?
It's interesting. Again, the OSI model is a logical concept. It's a model. So the network card actually works at both the data link and the physical layer.
One to correct.
Yeah,
Yes,
there will be some people out there, experts, that say no, the Ethernet card is at the physical layer, or no, it's at the data link layer. It actually works on both levels, on both layers, I should say.
Your